Hey guys, just going to go over the Newton's laws, weight and normal force worksheet that you got in class. My version looks a little different, just because I'm going off the online version that Mr. Hanbury and I were working on. I didn't format it, but same numbers, it'll be the same process, so that we can learn. So anyway, there's my cat. Might be able to see her. Oh, she'll probably find her way in. So. For question 1, we have an astronaut weighing 900 newtons on Earth. Key right there is on Earth. And then traveling to Mars, where we have a different G. This looks a little weird. That number is just another way to say newtons per kilogram. It's just another way to say meters per second squared. Doesn't really matter. So 3.6 meters per second squared is the same acceleration due to gravity. Mr. Hanbury just prefers to do it in newtons per kilogram. Really doesn't make a difference. So, what will be her weight on Mars? So we're looking for the Fg on Mars. We know that the Fg on Earth is 900 newtons. With the Fg on Earth being 900, that allows us to get the mass. Mass is going to be the force of gravity divided by the acceleration due to gravity. So in this case, it's 900 divided by 9.8. And 900 divided by 9.8 is 91.84. 91.84 kilograms. So this astronaut's mass, which is a property of the astronaut, will not change no matter where she goes in the universe, let alone just from Earth to Mars. This number is what we want to use to get her weight on Mars, because her weight on Mars, Fg on Mars, is going to be her mass times the acceleration due to gravity on Mars, and that will lead us to 91.84 times our 3.6, and multiply that by 3.6, you're going to get 330.61, depending on how you round, 61 newtons. So on Mars, she's going to weigh 330 newtons, where on Earth she weighs 900, but no matter where she is, her mass is always 91.84 kilograms. Cool. Question 2. You were told to change this so that it's 1400, not 400. So she's on the surface of Mars with a pushing off the surface. So astronaut is on Mars, and she is applying a force downward. Force applied of 1400 newtons. So she is pushing on the ground. Force of astronaut on ground equals 1400, and really negative 1400 newtons because it's down. Newton's third law says that the ground is going to push back up at the same exact force. Force of ground on the astronaut is going to be plus 1400 newtons. And the force of the ground acting up on the astronaut, well, that's just what we call the normal force. So the normal force, by Newton's third law, if she's pushing down on the Earth or the surface of Mars, the surface of Mars pushes right back up with her, on her with the same exact 1400 newtons that she is pushing down with. But their difference is, one is acting on the surface of Mars, the other, which is the one we care about, is acting on the astronaut. We care about what's acting on the astronaut, and that one is acting up. So her normal force is 1400 newtons. So from A, again, normal force is 1400 newtons. What will acceleration, excuse me, what acceleration will she experience upwards as a result? So, remember that there's a 1400 Newton normal force acting up on the astronaut. But we had the original force of gravity from question 1 of the 330.61 newtons acting down on the astronaut. So, to figure out the acceleration, we want to say that net force, which is the mass times acceleration, which is the sum of all forces, normal force plus the force of gravity. In this case, this can always be different. We could have tension, whatever. But in this case, this is the equation we want to solve. We know the mass was 91.84. 91.84 times the acceleration equals, our normal force is 1400, that's a plus, so because it's up, plus negative 330.61. So 1400 minus 330.61 gives us 91.84a equals 1069.39. Solve for a, and you're going to get, divided by 91.84, 11.64 meters per second squared upward. So, she is accelerating upwards at 11.64 meters per second squared. Gonna write that. Her acceleration was 11.64 meters per second squared upward. And for part C, it said for a time of 0.5 seconds. That was told to be added. So, how high will she rise into the air? We want to find D. But to do that, we've got to figure out, while she's in contact with the ground and accelerating upwards, we've got to figure out what speed she's going to leave the ground. Well, we kind of have to break this into two parts. The first part is when she's in contact with the ground, and then when she's off the ground. So, in contact with the ground, she's starting at 0. She has an acceleration, what we just found, of 11.64 meters per second squared. We want to figure out what speed she leaves the ground with. Sorry, not 0. We want to find the speed at which she leaves the ground, and that speed, that VF, is going to come over here as soon as, because this is when she's accelerating due to the 1400 Newton force. We want to figure out what speed she's leaving, so this VF on the in contact will be the speed that she's going to start with as soon as she's no longer in contact. So we want to find this, and yeah, this is a very tricky problem with our time of 0.5 seconds. By the way, this is not something I would ask you to do on the test. So VF equals VI plus AT. Our VF, I'm not going to, for sake of saving some space, I'm not going to show you what the VF is, but it's really just going to be the 11.64 times 0.5. So she's going to leave the ground with a speed of 5.82 meters per second. We want to figure out how high she goes. Her final speed at the top is 0. We're looking for D, and the acceleration. When she's off the ground, she's not accelerating at this. She's accelerating at the rate at which Mars is pulling things down, which is this number. So our acceleration is negative 3.6 meters per second squared. And when you solve that for D, VF squared equals VI squared plus 2AD, you're going to get squared divided by 2 divided by 3.6. 4.7 meters. She's going to go 4 meters off the ground. So hopefully that kind of helps. She's in contact with the ground for a little bit. That's when her force is 1400 newtons due to the normal force of 1400 with the force of gravity that we just found to use this acceleration. Use that acceleration and the time she's in contact with the ground to figure out the speed with which she leaves the ground. The speed with which she leaves is our VI. It's a different VI, obviously. And we can find our distance. All right. Number 3 shouldn't be too bad. We have a mass of 1,000 or 10,000 kilograms. Takes off from Mars. So Mars is still a clue. That's telling that our G is negative 3.6 meters per second squared. There's our force. That is our force of thrust. What acceleration? So we have our free body diagram. The rocket has weight. Has to overcome that weight. The weight is going to be the rocket's mass times the acceleration on Mars. So 10,000 times 3.6. So 36,000. With a thrust of 120,000. So our net force, mass times acceleration, equals force thrust plus force of gravity. See that this equation kind of looks familiar each time, just labeling these forces differently. So our mass 10,000, solving for A, equals thrust 120,000 plus negative 36,000, and we solve that for A, 120,000 minus 36,000 divided by 10,000 to get an acceleration upwards of plus 8.4 meters per second squared. All right. While I'm right here, the apparent weight of the astronaut, if she is a passenger. So, remember that our astronaut had a mass of 91 point, I believe it was 8 kilograms. Might be 91.6, I just don't remember, don't have it written down. The apparent weight is the normal force, so we have the mass times the acceleration equals the normal force plus the force of gravity. We're talking about the astronaut, so we're going to use the astronaut's mass, and I'm just going to bring all this up here so we can see it. So all this, just bring it up here. The astronaut's mass, 91.8 kilograms, times the acceleration, well, we just found that, that's 8.4 meters per second squared, equals the normal force, aka the apparent weight that we're solving for, plus the force of gravity, and the force of gravity that we found was from part A, 330, again, I'm doing this from memory, I think it was 330.4 newtons. And we want to solve for the normal force. I won't go through the algebra, but 91.8 times 8.4 plus 330.4. So her apparent weight is going to be 1,100, roughly 1,100 newtons. So she's going to feel a lot heavier. And we know that anytime something's going up, they're going to feel heavier. Okay, and number 5, we have I'm going to do number 5 up here just because it's a little low, so it's easier for me to do it up here. Number 5, we have a 10 kilogram crate being pushed with 30 newtons. So 30 newtons, the astronaut is doing the pushing. Newton's third law says that the astronaut is also going to feel a push of 30 newtons. Astronaut pushes on box, box pushes back on astronaut. The astronaut has a mass of 91 point whatever kilograms. The box has a mass of 10 kilograms. So on the box, there's one force. The net force on the box is 30 newtons, which equals the mass of the box times the acceleration of the box. So 30 equals 10A. Our acceleration of the box is 3 meters per second squared as drawn to the right. That's part A. For part B, it's the acceleration of the astronaut. You're going to set it up. We're going to run out of time, but it's 30 newtons equals 91 point whatever 3 kilograms times A. Solve for A, and you'll get your answer. So we'll go over this in class if there's any more questions. Thank you.